Robots have the potential to significantly improve the lives of those who need physical assistance, and for many individuals with substantial mobility impairments, this assistance often occurs while they rest on a bed with blankets and sheets covering the majority of their body. As a result, bedding manipulation around people is a key skill for robust robotic caregivers to have. In this work, we show how models trained entirely in simulation can enable a real robot to uncover a blanket from target body parts of a mannequin person laying in bed without uncovering the rest of the body. In the simulation environment for bedding manipulation, we allow a human model to settle on a hospital bed in a supine pose with some variation in its joints positions. Then, we discretize the body into target and non-target points before dropping the blanket over the person. We modeled the robot's end effector as a red sphere that is able to interact with the cloth. Given an observation of the human pose, the robot selects an action to uncover a target part of the body. We model actions for the bedding manipulation task as 2D grasp and release points. The robot first grasps the cloth at the grasp location, lifts the cloth to a fixed height, moves its end effector linearly to the release location, and then finally drops the cloth. We compute a reward value in order to train policies. This reward value incorporates positive rewards for uncovering target parts of the body and penalties for uncovering non-target parts of the body, covering the head, or for choosing grasp and release points that have excessive distances between them. We introduced two formulations for learning policies for bedding manipulation, one using reinforcement learning and the other using self-supervised learning with optimization to generate training data without human intervention. We train policies for uncovering 6 different target body parts. When training these models, we assume that the human model has a fixed body shape and that the blanket drops onto the person from a fixed initial position. We evaluate our policies over 100 randomized rollouts in simulation and observed that both the RL and self-supervised learning models were able to reliably uncover most target body parts. However, some target limbs, like the left arm, were particularly challenging due to the proximity of these limbs to other non-target body parts. We then break the assumptions made in training by evaluating how well policies generalize to varied initial blanket states and varied human body shapes. We found that performance was consistent across the generalization cases for a few target body parts, but observed noticeable drops in performance for others. This suggests that there's room for future advances towards robust bedding manipulation that is adaptable to changes in human body shapes and blanket states. Lastly, we evaluated the simulation-trained RL policies using a Stretch RE1 mobile manipulator to uncover target body parts of a medical mannequin lying in a hospital bed. The performance achieved in the real world is generally consistent with that seen in simulation, indicating that sim-to-real transfer of policies for bedding manipulation around people may be viable.